There's a visual tool called Phasor diagram that are frequently used for analyzing AC circuits. So in this video, I'm going to talk about this, what the diagram is, how to read the information from there. And in separate videos, I'm going to talk about the use of the Phasor diagram for analyzing different circuit elements in an AC circuit. But here, I'll talk about the Phasor diagram. This is basically a diagram that enables us to deal with this trigonometric part of this alternating EMF, alternating current expressions. So just keep this in mind. Well, what is it? There's a cosine factor in here. What we do is basically we think of this as the x component of a two-dimensional vector. So we just imagine a vector in here. We are going to call this as EMF vector. So I'm going to draw a vector sign over the top of it. So that's imagined. Just keep this in mind. Its magnitude is equal to epsilon 0, which is the amplitude. And the angle that this thing makes with the horizontal axis in here, I'm going to call as the x-axis, and this is the y-axis, is omega t plus phi. All right, so that's basically an imagination. But what happens in here is that the x component of that vector would then be the real EMF, real time-dependent EMF, which is epsilon 0 times cosine omega t plus phi. That's basically this one, so that's the real one. All right, just keep in mind that this is the magnitude of the vector that we are talking about in here is the amplitude, which is epsilon 0, and the angle of the vector is basically omega t plus phi. So it contains the phase angle plus this time-dependent factor. All right, so the nice thing in here is that we basically have a picture where we have a vector of fixed length, which is rotating around the origin with a constant angular velocity. So now we can then interpret omega as angular velocity instead of angular frequency in that picture. So since this motion is a very nice motion, it's a constant angular velocity motion essentially, of not a matter, of course, some kind of an imagined vector, but still this is a thing that we can easily understand. And at any given time, we can also, from the orientation and the magnitude of the quantity, we can easily find the real quantity in here. So as a result, this is a very easy to use tool. So later, of course, we are going to use this tool to discuss several things. In here, I would like to just set some of the essential terms. So let's just start with this. So let's just do it like that, all right? So we have these two expressions. One of them is the real EMF, right? Which is, I don't know, it's a sinusoidal curve like that. I cannot draw this perfectly. And this Phasor diagram. Right? Just remember that in the Phasor diagram, this is just an imagined thing. So as a result, there are some unreal, unphysical things in there. So this is just a tool to understand what's going on the real thing. Okay. So as a result, we have a vector that basically rotates with constant angular velocity around this origin in here. So we can then associate certain times on the Phasor diagram with the certain times for the real circuit. So first, let's just say that, right? I'm going to use a different color for the vector now. So there is this special instance where the EMF becomes oriented parallel to the x-axis. So let's say it like this. This is at time t0, let's say. This is the point where the real EMF becomes a maximum. right? Because this is the point where the x component of that vector has the maximum value, which is the amplitude, basically, right? So let's say that, I don't know, there's this point in here where this EMF becomes anti-parallel to the x-axis. Let's just say it like this. This is at time t0 prime. And so this is the moment where the EMF becomes minimum. So there is this special place where the EMF is oriented along the y direction. Let me call this as at time t1. So this is the point where the x component becomes 0. So that's the point where the real EMF vanishes. So that's the time t1. And there's another time in here. So let me just call this as t1 prime, in which case it is that point where the EMF again becomes 0 one more time. So this all of this happens within a period. So you can also see the periodic thing in here. So therefore, after one period, so this is the point in here, right? The time is now t0 plus 1 period. So just keep in mind that we usually use the angular frequency as the only variable. So therefore, we would express the period as 2 pi divided by the omega, right? So as a result, the time changes on the phasor diagram, but usually this is the part that we are not that interested in. In any case, the time also changes on the real, I don't know, position, real EMF versus time graph. So I should have actually put the time argument in there. So let me use the white color for doing this. So what we do is, by just looking at the phasor diagram, we think about the real thing, right? So as a result, this is one of the things that we should do. Since the phasor diagram is not real, we have to translate what's happening on the phasor diagram to the real thing. There's one situation in here where we have like, I don't know, we have a circuit where we are talking about EMF, and then there are these circuit elements and I don't know, lots of different things. And the current in here, let's say, I'm considering these two quantities, for example, and it might happen that, well, it is definitely the case that all of these circuit elements, all of these quantities have the same frequency, right? So omega is going to be the same, but they might have a different phase. So as a result, we might have a situation where the EMF is basically cosine of omega t plus phi, and the current is I0 times cosine of omega t plus phi prime, let's say, right? So if I draw both of these quantities on the phasor diagram, how do they look like? So the EMF is going to look like a vector like that, and the current is going to look like a vector like this, right? Where this angle is omega t plus phi, and this angle is omega t plus phi prime. So on the phasor diagram, these two vectors are the vectors that rotate with the same angular frequency, angular velocity, which means that the angle between these two vectors actually is constant. So I'm going to do it like this. So this is phi minus phi prime. So as a result, I can perhaps erase all of the details, the other details in here. So what we have is essentially two vectors with fixed length, constant magnitude, and a constant angle between them. Sorry about this. The angle is phi prime minus phi. So I'm using a picture where phi prime is bigger, slightly bigger than phi, right? So let's try to understand it like this. So that means, I don't know, let's say at a later time when the current is like that and the EMF is like that, we will still have these two vectors, but we will still have two vectors that have the same angle between them, which is phi prime minus phi. So let's say it like this. This is at time, I don't know, t prime, let's say, where the current is along that direction and the EMF is along that direction. But they still have the same angle between them. So as a result, these two vectors, they rotate together on the phasor diagram. All right, then we will translate some of the things. So, and then we have the points where they are maximum or minimum. And let me add one more thing in here. I have talked about the time as an argument that we can choose freely. So it is possible to choose time, to redefine time, the starting point of the time, so that one of these phases are going to be equal to 0. So it is possible to make, for example, this phase to be equal to 0. I don't know. So this essentially implies that, well, this becomes 0 in here. So I'm just going to erase this, right? So we have, this is going to be cosine omega t, but this time the current would have a phase angle, which is phi prime minus phi. So in this case too, what's important is the phase difference. So I can, by the redefinition of time, I can change the phases, but the phase difference is going to be the same. So in this kind of a picture, omega t is the angle of the EMF, and omega t plus that phase difference is the angle of the current. This simplified picture is a little bit easier to understand. So as a result, in the next picture, I'm just going to talk about this situation in here. Right? So as a result, I'll talk about the EMF. I'm just going to assume that, sorry about that, somehow the color has changed. The EMF is equal to epsilon 0, E0, cosine of omega t. And let's say that the current is I0 cosine of omega t plus phi prime minus phi. All right. What I am interested in here is the times where these things become maximum. Right. So as a result, I'm just going to think about the situation where, for example, the current becomes maximum. So that means there is a moment in time in here where the current vector is aligned parallel to the x-axis. At this point, the EMF would be pointing like that. And again, the phase difference, the angle difference between them is phi prime minus phi. So if I draw this on a quantity versus time graph, so this time I'm going to draw them in with different colors. So the EMF is cosine omega t, so therefore it's a maximum at t equals 0. So it has a graph like that. So that's the graph of the EMF, right? I'm going to use a different color for the current. This is going to be something like that. There's some kind of a phase difference between them. So what happens is that, let's just look at this situation in here. This is a time where the current becomes maximum. So that's let's just call this time as, I don't know, let's say T1. This is the time T1 where the current is aligned with the x-axis and EMF is not yet aligned with the x-axis. But you can see that in the phasor diagram, when time passes, these are going to rotate, and then after a little bit more time, the EMF would be aligned now. So let me then erase this and then show what happens when this thing happens. So this is a moment in time where the EMF would be parallel to the x-axis, and the current would be like that. So that's the current vector, the EMF vector. So that's the time t1 plus delta t. So it is that time in here. So slightly later at time t1 plus delta t, this time the EMF becomes maximum. So again, this is phi prime minus phi. So as a result, if that's the case, if phi prime is bigger than phi, so that angle is phi prime minus phi is positive. In which case, first the current becomes maximum, and then the EMF becomes maximum. So you can find the time difference in here as delta t. I want to cut this thing short, so therefore you can easily see that this is basically this angle difference, the phase difference divided by the angular frequency. You can easily see it by using this trigonometric functions in there. All right, just keep this in mind. So I can also relate this time difference for other things, like, for example, the time difference between, for example, the current becoming zero and the EMF becoming zero. So at these two times, for example, so let's say that this is the T2. T2 is the time where the current becomes zero. And so therefore, slightly later, the EMF would become zero. So how would that look like on the phasor diagram? I'll just try to draw them like that. So when the current becomes when the current becomes zero, that means the current is aligned along the y-axis, positive y or negative y, whatever. And the EMF is like that. So we still have the same angle in here. So that's at time t2. So just a little while later, of course, this is going to rotate. So therefore, we will have a picture where, right, let me redraw this. So the current would be oriented like that, and the EMF would be oriented like that. So right at that moment, where the time is now t2 plus delta t, the EMF becomes zero. So as a result, on this diagram, there are some interesting moments where something happens. There's a time difference between these things. So first the current becomes zero and then the EMF becomes zero. That's one special situation. Or first the current becomes maximum, then the EMF becomes maximum. Or in here, for example, first the current becomes minimum and then the EMF becomes minimum. Whatever. So there's always a time difference between them. Okay. So there's a terminology that we use for that. So this situation where the current is ahead of the EMF. So let me call that angle as, it's the same again, phi prime minus phi, right? So we say that the phase difference between current and EMF is phi prime minus phi. We say that this is the phase difference between them. It's actually a time difference, but of course this doesn't explain which one is ahead and which one is behind. We say that current leads EMF by phase difference phi prime minus phi. We say that the current leads EMF, or we say that the EMF lags behind, or just lags current, again by phase difference phi prime minus phi, right? So the phase difference basically has a real physical meaning that I have explained in here. So there's some kind of a time difference between these two signals. So you can analyze this time difference perhaps for the position versus time, or the quantity versus time graph. Quantity versus time graph, but this is usually difficult, and this is quite easy to see on the phasor diagram, where everything is very simple. So we just have two vectors with a fixed angle between them, and it's just rotating around the origin.